Building Services Overview Part 3. In this session, we look at air distribution, heat recovery, electrical supply and distribution, power factor correction, and voltage optimization. Now, the first system we're going to look at for air distribution is single duct VAV. Now, it's an all-air system in which the volume of air supply is modulated to match the cooling demand. So it's an all-air system. Outdoor air is delivered to the air handling unit, goes through the filter, either through the cooling or the heating, but it goes through both coils depending on which one's on at the time, arrives at the VAV valve. The VAV valve is controlled by a thermostat in the room, usually connected via the BMS, and then the air is extracted out and exhausted out to the outside. It can be, a certain amount can be recirculated as well. If we look into the sealing space, we'll see there's no pipe work involved. We've just got an extract duct and a supply duct. The supply duct feeds the VAV terminal, and that allows the air to be regulated at that point. So the VAV terminals, or VAV boxes as they're sometimes called, tend to come in all shapes and sizes. We can see there on the different diagrams, all controlled by an actuator on the side. Usually, if it's like a Trend system, it will say Trend or Honeywell or whatever. They're connected to the BMS, and the BMS will control the air delivery for that area. Now, dual duct VAV is similar to single duct, but it's now got two ducts. It's got a hot control duct and a cold control duct. This has got the benefit of being able to do heating and cooling simultaneously in different zones. The main drawback with single duct VAV, it could only do one thing at a time. It couldn't do heating and cooling. This system will do heating and cooling in different zones there. So the air arrives into the VAV box, and we decided whether or not it's going to be hot or cold. And we can see on the picture there at the bottom, we're showing a mixing damper. It's essential to make sure this mixing damper is operating correctly, because we don't want leakage between hot and cold or cold and hot, therefore delivering hot and cold at the same time, because that would be quite wasteful. More duct work in the ceiling, still no pipe work involved. We've got the hot supply duct, the cold supply duct, and the recirculation or exhaust duct there. Quite a lot of duct work though, and again, like we said earlier about the single duct VAV, pushing all this air through duct work is quite energy hungry. So generally these systems consume quite a lot of electricity, so therefore are not particularly efficient. Now, if we want more control over the air that we have in our room, or more control over the temperature, we can use constant volume. So this delivers air at fixed fresh air rate, but we can vary the temperature. Whereas on the VAV, we can vary the volume, but it's a fixed temperature. So this is a simple CAV system. The airflow is constant, but the supply temperature is varied to meet the thermal loads of a space. Now, this suits areas where we want a specific need, where it might be a kitchen, an operating theatre, a laboratory, somewhere where we don't want to mix the air with other areas. So if we've got an area with a specific need, we can use a constant volume system that just suits that particular area. Now, lots of older buildings use fan coil systems. Still get them in some new buildings, but not as common as they used to be. Now, a fan coil system, instead of the hot and cold air being delivered by the ductwork, it's now being delivered by pipe work, water pipe work, arriving at the fan coil terminal units. So we still get fresh air coming into the zone by the air handling unit and smaller ductwork. And because it's smaller ductwork and smaller air handling unit, it tends to be a more efficient system, because we're not using so much energy to push the air along the ductwork. The air arrives in the area where the fan coil systems are operating, or sort of usually above the false ceiling in like what we call a plenum. So we're providing fresh air to the zone, but the fan coil units recirculate room air. So they constantly recirculate the room air, and the actual air is topped up with fresh air from the air handling unit there. The fan coils receive hot water from boilers and cold water from chillers, and they also contain filters, fans and actuators. Simple device a fan coil unit is, consisting of a heating and cooling coil and a fan. The fan coil is typically not connected to the ductwork. The ductwork just feeds fresh air into the zone. Due to the simplicity, fan coil units are more economical to install than ducted or central heating systems with air handling units. However, they can be a little bit noisy, because remember on the VAV system, the fan is actually at the air handling unit. Here we've got a fan in every area. So if the units are not maintained correctly, fans can tend to get a little noisy. Most of the time these units are concealed. They can be exposed, can be wall mounted as well, typically installed within an accessible ceiling there. So the fan coil receives its hot and cold water from central plant, and they're controlled by the S there. And we can see the fan coil units are quite numerous there, even in that picture there, which probably represents perhaps 10 or 12 meters. We've got 3 units, and you quite often find in buildings we may have upwards of 500 to 1,000 units there, and quite heavy on maintenance because there's lots going on there with the piping, the filters, the fans, the actuators, making sure the condensate pipe is kept clear. Now, where we do have ventilation, it's essential that we use heat recovery. So heat recovery, even with recirculation, fresh air needs to be brought into the building and either be heated or cooled. Energy can be saved from transferring heat from the outgoing airstream to the incoming airstream. Since all buildings require a source of fresh air, we could actually do this. We could bring in fresh air from windows, but when we do that, we let out all the heat. We could just use mechanical ventilation and extract, but again, we waste all the heat. If we think about UK building regulations require one air change every 2 hours, that means that we're actually swapping the air in the building 12 times a day. Well, what we don't want to be doing is throwing away the heat 12 times a day. We want to heat the building at once, swap the air in the building so people can breathe and have fresh air, but hang on to that heat. So how can we do that? Well, heat recovery devices can be standalone devices that operate independently, or they can be built in or added to existing HVAC systems. Now, in a small building in which every room has an exterior wall or has access to an exterior wall, heat recovery device can be a small standalone unit, perhaps in the roof space or perhaps in an adjacent room there. Now, a large building will require either many small units or a large unit connected to the centralized system. Now, one of the things we use is a plate heat exchanger, and makes it possible to transfer heat between the 2 airflows. It's low cost of installation operation, complete separation of airflows, which is a good thing, absence of moving parts within the heat exchanger itself, products with different sort of suitable for different environments, as it were, low pressure drop, high efficiency, easy to clean, minimal maintenance, and effective for noise. So how do they work? Well, you imagine that the air is extracted from the building. This is the extract air coming out our office, passes through the heat exchanger and exhausts out cold. So it leaves the heat behind in the heat exchanger. These are generally around about 80% efficient. Fresh air comes in from outside, picks up the heat that was left behind, so 80% of the heat was left behind in the heat exchanger, picks that up and then goes into the supply ductwork. Because we're losing 20% of the heat, we need to quite often have a little bit of a heating coil or a booster coil in the supply network there, just to retemper the air so we're not blowing cold air down people's necks. Now the smaller units, as we can see, is a filter out of one on the right hand side there, tend to sit above the false ceilings and perhaps in cupboard areas, and we don't always know that they're there. These are small ones that serve individual rooms. These have filters built into them, quite difficult to maintain, and in my experience, quite often they're not maintained very well at all, because the filters are quite difficult to get out, and these are quite often in places difficult to access. So the Mitsubishi equivalent of those is called a Losnay unit. If they were Daikin, they'd be called VAM units. And we can see the heat exchanger cartridge sits inside and quite often has filter medium attached to it. The filter cartridge needs to be taken out to be cleaned. So just to recap in that office there, the outdoor unit, this is the VRF unit outdoor, which is often used in modern offices for doing heating and cooling. See, it's providing the heating air there. Now remember, this air is just room air that's recirculated. In this system, the air in the room never changes. But this particular unit is linked into a Daikin VAM unit. And we can see on the Daikin VAM unit, it's taking out the stale air, bringing in fresh air and distributing that nice green coloured there, fresh air into the room there. So the fresh air is coming in via the heat recovery unit and heat recovery ventilation VAM unit, and the heating and the cooling is done via the VRF system. Electrical supplies and distribution. Now, all our buildings rely on electricity, and we probably don't think about it too much, but where does that electric come from? Well, most of the time it arrives at our building at quite high voltages. It arrives also from power stations. Now, those power stations we always find on the coast. Now, it's worth thinking, why are they situated on the coast, or why are they situated near watercourses like rivers? Well, they're situated near water, so they can actually disperse some of their excess heat to the water, whether it be sea or a river or a canal or something. And that's actually quite wasteful, because we've got all that energy going into the generating station and we're rejecting quite a lot of that energy in wasted heat to water. The residual energy goes into a turbine which produces electricity, which goes into usually a transformer. The generating station generates electricity at about 1,000 volts. Well, for distribution, 1,000 volts is quite low, mainly because of volt drop, which happens in the distribution system. So we need to transform that up. And in this country, we transform it up to around about 500,000 volts, 500,000 volts. We transport it at 500,000 volts, but of course we don't want it at 500,000 volts when it arrives at our building, and we transform it back down again. And in fact, by the time it arrives at our customer, our school, our warehouse, our university, or places like that, it's probably been transformed down 5 or 6 times. And every time we do that, we lose energy. Use energy mainly through heat in the transformer. We've probably all seen these as we drive around the country, or perhaps see them in city centres. Not overcommon in city centres, quite often in more rural areas, just outside city centres. And these are substations. These actually take the voltage in, take the electricity at quite high voltage and transform it down. And we can see on the transformer here, we've got fans and radiators here, and this is to disperse away the excess heat. Now, the consequence of doing all this, rejecting the heat and dispersing away the heat, currently 54% of the electricity of the energy used to produce the electricity is lost by the time it arrives at our UK home business, where even further losses occur. So in real terms, we're probably losing about 60% of the energy. So although grid electric is convenient, it's actually really wasteful, because we're wasting about 60% of the energy used to produce the electricity. And because of that, that's why the carbon emissions of electric is quite bad, and why generally electric is quite expensive, because it's quite a wasteful process producing electricity, albeit at power stations. Now what we ought to be able to do is produce the electricity ourselves. Now we can do that in various ways, like we looked at in previous sessions, using a CHP that will produce electricity, and also we can use solar PV, we could use wind turbines, and all of these things don't have the associated losses like producing electricity at a power station. When it arrives at a building, it arrives generally in three-phase electric power. Now I would imagine most of you are familiar with the term three-phase electric. It's a higher voltage, which we don't want to use in our offices, but we might want to use in our factories. We use the three-phase power, the higher voltage, to power large motors and heavy loads such as things like compressors, chillers, and stuff like that, and large water heaters. We use the single-phase loads to connected things like lighting and small power. So we come in three phases: line 1, line 2 and line 3. Colours there shown red, yellow and blue. The newer colours are now brown, black and grey to fall in line with European colouring there. The voltage between any two of those phases, any two of those lines, is 415 volts. The voltage between one of those lines and the neutral, shown there as black, is 240 to 230 volts. So that's where we get the single phase from. So single phase is any one wire and the black, and three phase, or the 415, is across the three phases. Now when we look at the colouring of the wire in our buildings, it can be a little confusing for us sometimes, because our older colours were red, yellow and blue, black for the neutral, green and yellow for the earth, and any single phase loads were actually red. But the newer colours are brown, black and grey for the phases, blue for the neutral, green and yellow for the earth again, and any single phase loads are brown. Now it still works okay like this, but it can get quite confusing because some older buildings will have the old wiring and the new wiring as well. There's nothing wrong with the old wiring, it's just the colours don't fit into modern sort of colour schemes. It was changed because of going in line with Europe. I think we're going to have to live with this probably for many years. We're probably not going to change this wiring, but any new wiring installed now is the new colour system, and any old wiring tends to be the older colour system. If we've got two colours in a board, or two wiring systems in a board, we should have a label on there stating that be aware that there is two colour schemes. Now when the electric arrives at our building, it generally comes into some sort of switch room. Now the switch room is probably somewhere we're not going to visit unless we've got an electrical bias, as it were. But it goes from the switch room to distribution boards. Now the distribution board probably is somewhere we'd visit, because if our electric trips out or switches off for some reason, it's usually because one of our circuit breakers has failed. Now the main circuit breaker on this board here operates all the circuits within the board. The individual circuit breakers underneath switch individual circuits such as sockets, lights, water heaters, compressors and stuff like that. So if we have a fault on any one of the individual systems, it switches off that system to isolate it to make it safe. Now on the more domestic style ones, as we can see there, still work on the same fashion. The main switch switches everything off, and then we've got the individual circuit breakers. These switch off individual circuits, and these are all protected by something called an RCD, a residual current device, and this is there to protect people against electric shocks. Now the distribution boards can be small commercial or public installations there, usually single phase supply inside the units themselves. And we can see on that unit there, it has a three-phase main switch, and single phase loads, we can see on the top right there, come out of this board, along with 3-phase loads as well. If it's a 3-phase load, the circuit breakers are usually linked together. So when we switch it, we switch all 3 at the same time. We can see we've actually got newer colours in here as well. We've got a blue neutral. So normally in here, most of the neutrals are black, but we've got a newer neutral here, and the electrician has actually put some black tape on this to give us an indication that this is actually a neutral and not a new phase colour. Now, years ago, before we had circuit breakers, we had fuses. Now, fuses didn't give us the same sort of protection as circuit breakers. But one good thing about fuses, it made us think a bit more, because it's very easy to reset circuit breakers, whereas we have to take the fuse out, rewire it, or put a new cartridge fuse in, or if you've not got one, go down the shop and buy one, put wire in it and stuff like that. We think about the fault rather than just keep resetting it, because with circuit breakers, we tend to just keep resetting it, thinking the fault might go away there. We can see the colours dictate red a 30 amp, blue 15 amp, white 5 amp, and the different size cables getting larger from the right, smaller from the left there. These are the smaller loads like lighting, water heating, going on to ring mains and going on to probably cookers or perhaps an electric shower, obviously in a domestic location there. Now the fuse board on the right, albeit a small one, shouldn't really have any of these in your buildings now, but if you have still got the odd ones, think about the fact that these contain asbestos. Behind the fuse carrier, these are rewirable fuses, and to protect the sort of fuse carrier from the little explosions or the red hot wire that used to happen in there, we tend to have a strip of asbestos. So if we've got somebody that visits that board quite often and does work on it, think about the fact that they could be exposing themselves to asbestos. So it's worth, if we've got one of these boards, thinking of getting it removed and replaced by a more modern board, hopefully with circuit breakers. Now, most modern boards now contain what we call RCDs, residual current device. And these actually, rather than tripping or rather than operating on overload, they look for what we call a current imbalance. So if we've got, for instance, 10 amps going out and only 9.9 amps coming back, we've got to think, where's that 0.1 of an amp gone to? And it's probably leaked down to earth. Now, what's more important for us is to think, where is it leaked down to earth through? Because it could have leaked down to earth through somebody's body, i.e. they've got the hand on the terminal and it's leaking through the body and the feet are touching the ground. And that obviously would kill them. So what we need to do, we need to make it actuate and trip out. What an RCD does, it looks for a current imbalance, typically 5 to 30 milliamps. That's 5 to 30 thousandths of an amp. And if it sees that imbalance in the circuit, it will trip the circuit, it will turn that circuit off round about 25 to 40 milliseconds. That's 25 to 40 thousandths of a second. So it turns it off instantly to stop people getting electric shocks. So it's worth remembering though, if our RCD does trip out, quite often when we go to reset it, it won't reset. So what we need, all of the circuits off, because they're off anyway, because if the RCD's tripped, and then our RCD then should turn back on and then switch these circuits on one at a time. And if it suddenly trips out when we get to the last one, that's where the fault is on that particular circuit. So whichever one trips out, that's where the fault is. You may find that all 4 will reset and then it will continue to operate okay. Anything that doesn't look right on an electrical circuit, it's worth reporting that to the electrical engineer on site. We quite often find that lids get missing and lids off circuit breaker boards and stuff like that because the screws get lost. So make sure that these lids are replaced, because potentially in here we could get overheating, and we don't want that causing fires outside. Failure to sort out electrical faults and failure to to actually take them seriously, which hopefully most of you do, can lead to fires and lead to loose terminals and stuff like that. It's generally loose terminals that cause fires in situations like this. If the terminal in the board is loose, there's more resistance there. The more resistance, the more heat build up, and potentially it could result in a fire, which obviously none of us would want. So the electrical circuits, they leave the distribution board and the circuits run around our building. Now, quite a few years ago, we used to use what we called radial circuits. And these are circuits or wire that left the distribution board, went round the sockets in the appliances and ended up at the last socket. The problem with that was, when we started to use larger demand on our appliances, larger demand on our sockets, by things like photocopiers and servers and stuff like that, by the time it got to the last socket, there was very little electricity left, so it sort of ran out of power. So what we do now, more modern wiring, we have what we call a ring main. It starts off at the distribution board, goes all the way round the sockets in a ring, and arrives back at the distribution board. So we get better distribution of electricity, because the electricity can actually go both ways round the circuit there. And we can see on this ring main here, using the newer colours, brown for the live, blue for the neutral, and green and yellow for the earth. Generally wide in 2.5 square millimeter cable, 2 core and an earth, the 2 cores being the live and the neutral and the earth, and protected either by a 30 amp fuse or more modern systems 32 amp circuit breaker. Now lighting's always a bit different. Lighting tends to suit individual buildings. Lighting was generally wide, using 1.5 square millimeter 2 core and earth, and protected by a 5 amp fuse or 6 amp circuit breaker. Lately though, wiring has been reduced to 1 millimeter because with the advent of LEDs, LEDs use considerably less power. So obviously power runs through the cables. The lesser power, the lesser the size the cables need to be. Right, another thing to think about in our electrical installation is power factor correction. Now, depending on what we've got in our building, or depending on what sort of building we occupy, power factor correction can make a considerable difference to our electrical consumption. So when connecting a voltage to a load, current is drawn, and we want that current and that voltage to be in phase. And if we look at a sine wave, we want them to sit on top of each other with no phase shift. And that, when we get that sort of phase shift, it's measured in what we call kVA. And if we're not careful, the kVA, kilovolt amps, can be more than the kilowatts. And if it's more than the kilowatts, we end up paying more consumption charges. So the ideal power factor is 1, where the voltage and current are in phase. And that's always the case on resistive loads. That's like electric heaters, old tungsten lighting and things like that. But as we start to move towards fluorescent lighting, LED lighting, things like motors, lifts, escalators, compressors, air conditioning units, things like that, we tend to get kVA rather than kilowatts. So therefore the use of kVA rather than kilowatts in building electrics such as transformers takes into account the current drawn, and the current drawn tends to be more on kVA there. So we can see on that diagram there that the voltage and the current are not in phase, and that's leading us to a power factor of about 0.6. Now that's quite a low power factor. If you had a power factor at 0.6, you'd be using considerably more energy than you thought you were. Things like some motors come with capacitors built into them, which tends to correct the power factor. So the way of correcting a power factor is with capacitance, either on the motors or built into a power factor correction unit there. We can see on this particular unit, this is a power factor correction unit, and if we looked inside the door, we'd be able to see banks of capacitors which were introduced in circuit to bring the voltage and the actual current back in line. This one we can see is ticking over at about 0.99, which is as near to 1 as it's probably going to get, and that's acceptable. When it gets below 0.95 or even 0.9, that means we're losing probably 10% of our energy there. If we're not careful, we're losing 10% more than we should be. So occasionally we'll have standalone units, or as this photograph or diagram demonstrates here, these are built in to the existing switch room. Again, we can see on this one, it's 0.99, 422 volts, 26 kilowatts and 37 amps. So if we're in our plant room at all and we notice, or in the switch room, and we notice the power factor running well below 1, it may be worth asking the question to somebody, what are we doing about this? And if you look at your electricity bill and it talks about a reactive charge, if you're being charged a reactive charge, that's due to a low power factor. So although you may not realise you've got a low power factor, look at the electricity bill. Does it anywhere mention a reactive charge? So power factors below 1 require the utility to generate more than the minimum volt amps necessary to supply the real power, which is why they charge you that reactive charge. For example, if a load power factor were as low as 0.7, the apparent power would be 1.4 times the real power. So we're actually using 1.4 times more electricity than we actually thought we were. And we end up with more losses on the circuit. Our cables need to be bigger, our transformers need to be bigger, and things like that, and everything gets bigger and more expensive. So power factors, anything over 0.95 is probably not worth getting over concerned about. But as we start to get below 0.95, 0.9 or even 0.8, then we ought to be concerned about it and try and take steps to correct that. Now, another thing we can think about on an electrical system is voltage optimization. A lot of the voltage that arrives in UK factories or offices or buildings is supplied from the grid, and it's supplied quite often in excess of 240 volts. 240 volt is the average supply voltage in the UK. But if we look at right at the bottom here, 220, that tends to be the voltage in places like Spain and Portugal and stuff like that. So if we go abroad and use our computer, our phone charger, or other small appliances abroad when we go on holiday, they work just as well on 220. So why do we put 240 volts into them? Well, the electricity board or the supply network tends to supply the voltage to the network well in excess of 240 to combat the volt droppage we get in the network. So some people that are near the distribution network start point get it at 250, and some people get it considerably lower. If we're the voltage too high, it may lead to premature equipment failure. It also uses more energy. If we're getting it too low, well, things can be problematic. The ideal voltage is round about 220 to 230. So it's worth having a survey done if we think our voltage is too high. Perhaps get an electrical company in that supply these voltage optimization units if you think it might be beneficial to you. But don't always think about installing a voltage optimization unit for the whole site, because there may be buildings on site that won't actually benefit from the voltage optimization. So if they're more like residential buyers, such as universities, halls of residence and things like that, they won't necessarily benefit from it. But areas perhaps in the university with lots of screens and high IT and labs and stuff like that, and perhaps air conditioning, that will benefit from it. So only put it in the building you think where it's going to benefit. So to look at that incoming voltage from the electric supplier, if it's more or around about 240 volts, the higher voltage could lead to equipment being overpowered and shorten its lifespan, and also will lead to increased cost. If we put a voltage optimization unit between the supplier and our network and our supply, we reduce the voltage, prolong lifespan of equipment, and potentially save more energy and cash in the meantime. So thanks for listening. That covers us for today, and we'll see you on the next session. Thank you.